Hello, everyone. Welcome to our next module in our Deep Learning Do It Yourself course. So today we will be speaking about transfer learning and self-supervised learning. So these are two types of techniques of learning or doing the best you can in the face of little annotated data. So which is quite common in practice, as you'll see during your internships and during your future projects. And we will be discovering today some techniques to allow us to still be able to use deep learning even when we don't have much annotated data, or we don't have many computational resources. So we will be addressing today these types of cases. Into more details, we will be speaking today about transfer learning at large, the scope, and what do we mean actually about with transfer learning. And then we will be seeing how we can use off-the-shelf networks, meaning that a network that is already pre-trained, how can you use it yourself for different tasks without actually touching on the weights of this network. Then we will be talking about fine-tuning, meaning to adjust a bit the weights of the network for a new task. And we'll be seeing some other ways of transfer learning, meaning task transfer learning, when you transfer from one task to another in a sequential manner, multitask learning, when you train for multiple tasks at once, and domain adaptation, when you train on one type of data and then you want to adapt your model to some other ones. And finally, in the next video, we'll be speaking about self-supervised learning, which is a bit of a larger topic, and concerns a more recent family of methods. But now we'll be beginning with transfer learning. Let's set the common grounds and the vocabulary for this topic. So in transfer learning, we always assume that we have two data sets: a data set S and a data set T. S stands for source and T is from target. So the data set S, we assume that it's fully annotated and that we have plenty of images, and we can train a big neural network on it. Right? So we have our CNN S that we train on this data set S. Now the data set T, the data set target, is actually our data set that we want to work on, and usually is not as much as annotated, and or it has in generally fewer images. And in some cases, the annotations from T do not necessarily overlap with S. I mean, most of the cases actually. So in transfer learning, the whole idea is that we can use this first model CNN-S, so our deep neural network trained on the large amount of data, to learn a better CNN T for the task T. So in a nutshell, this is what we try to do with transfer learning. So even if our data set T is not large, we can actually train a CNN for it, or by pre-training a CNN on data set S. And then what we can do is either fine-tuning, which we'll discover in a subsequent section, or just use the CNN as a feature extractor. So this is what we'll discover at first. Just to have a comment on that. So in general, you'll see during your interviews for internships that this transfer learning concept is used loosely. So there can be a lot of things that can be considered as transfer learning, and the whole goal of this course, this module, is to show you that it can be more nuanced, and that there's some different families and types of approaches that you can actually have in transfer learning, and we'll just provide you the tools for better tackling this. So why using a pre-trained CNN off the shelf would be a good idea? I mean, we just trained our network on ImageNet, and now the idea here is just to take it after training on ImageNet and to use its features. So I will be showing you why it can be sometimes a good idea, and actually how to use off the shelf CNN networks. So a first application where we could use these CNN features is for image ranking or for image retrieval. So assume we have here an image with a certain height and width and depth. So here is 224 by 224, the depth. And we have our AlexNet or VGG16 network that was trained for classification. What we can do is to pass the image through the network and just take the output of the last fully connected layer, which is a global descriptor of dimension 4000. We just have a one-dimensional vector of length 4000. So we can do the same thing for VGG16. So I'm here just for as a reminder. I'm putting the architecture of VGG16, which is very similar to the one of AlexNet. So you remember we have these five convolutional layers, followed by a few fully connected layers at the end, and then our 1000 output, which stands for the 1000 classes of ImageNet. So when we look into more detail, if you remember this diagram from a chart from the previous lesson, our vector of interest is somewhere here, where we see we can have an output of size 4000. Previously in convolutional layers, we can see we have spatial dimensions. So we have outputs of the size 14 by 14 by 512. And if we're earlier in the network towards the bottom, 56 by 56 by 128. So they're bigger in spatial resolution the closer they are to the input. So assume that we did that for all the images in our data set. And now we can use what we call the query by example. So we can use the vectors, the features from one image to compare it with all to do the compute the Euclidean distance with all the vectors from the data set and do a ranking by increasing order of distance. So the closest images should have a smaller distance, well, close to 0. So we can see that actually doing this on CFAR is actually not so bad. So we can see that we can retrieve similar images similar objects, right? So here we have this purple flower or other purple flowers. Here we have different instances of elephants, of boats, of Halloween pumpkins, and of dogs. So it's actually not this bad in terms of capabilities. People notice that actually when you do this, you take the features from this last layer. Features tend to be more semantic since they're closer to the last classification layer. So you might have not exactly the same object, right? So here we have different pumpkins, but we don't have exactly the same pumpkin. So sometimes you might be interested in having exactly that, right? Or retrieving the same object. So in order to do that, researchers went on taking features from some lower parts of the network before the fully connected layers. So actually, we can sample information from feature maps. So here I'll take the example of a VGG16 network for which the last convolutional layer has 512 channels, and the H and W here are 7 by 7. So what we can do now is what we call global spatial max pooling. We can actually even do the sum, but to the first approach concerned max pooling. So what we do, we have our 512 feature maps. So on each feature map, we take the maximum value, which corresponds to the highest activation in that feature map, meaning that the most salient part of that feature map. So we do that for all the K feature maps. So we have at the end a K length vector. So K here is 512. Well, we can do some other post-processing tricks as common in this area. The most important one is L2 normalization. So we want to normalize our vectors to be to have the norm of 1, the L2 norm of 1, and this allows us better comparison between the vectors of the dataset. What also helps is to do PCA and whitening to decorrelate the dimensions of these vectors and then normalize again. And we call this approach MAC, maximum activation from convolutions. So as stated before, this is what we take, right? So in each window of 7 by 7, we have 512 of those. We just take the maximum value. So we reduce the size. We convert it from a 2D vector to the feature map to 1D vectors. So we can see that actually this makes sense. So these are some results on using features from a network trained on ImageNet and then tested on a high resolution dataset of images from of buildings from Oxford. And what we do here, we take the position of the maximum for a certain feature map in each of the two images. So assume that this is the feature map 0 in image 1, in this image on the left, and this is feature map. This corresponds to the maximum of the feature map in feature map 0 in the image on the right. So we can see that they kind of go into similar parts of the image. They tend to activate in the same place. Now let's take feature map 1 from image on the left, the position of the maximum that we selected, and feature map 1 on the image on the right. And again, we can see that it's a kind of a similar spot. So it's, to some extent, it fires on similar patterns. So we could actually match these two images. Similarly, for this square or the green square on this part of the images, and the green one here, which corresponds to a part of the statue and the arcade of the door. Right, and we see this repeating across several images. Same here for the green for the red feature map here is activating on the column. Here the blue and the green one are activating on this pattern from the building, and here the cyan one, it seems to be covering two these crowns of this type that we see here. So it's actually quite meaningful, and we see it repeating in different types of buildings. Again, you can see the cyan here on this window activating, even though there's some differences in pose between the two images. Also here we can see on the chimney from the red feature maps that they both activate on the chimney. So this was actually the first approach for that, and it was quite simplistic. And the authors, being encouraged by this locality, they said, okay, maybe we can have multiple patterns on the same feature map that would be meaningful. So they went to invent what we call the regional MAC, RMAC, regional MAC spooling. So here we have practically the same pipeline. We feed an image, we stop at the last convolutional layer, COM5, but instead of just selecting one, the position of the maximum value, what we do here, we take different squares. So we take multiple patches on each feature map and take the maximum inside this small patch. So we have a big square from where you take a maximum. Then we have this square here from where we take another maximum. This one here, and this one here. So well, this is a simple example where we show for 5 patches. So the big one and the 4 one in the inside, and we end up with the different vectors of size k. And we do, as usual, we do the post-processing, L2 normalization, and optionally some PCA and whitening, and then again L2 normalization. And to make things easier, what we do, we just sum them. Right. So again, we have again one vector, but now it contains a bit more information than the original MAC, because in the original MAC we had information just from one activation, while here practically we aggregate from different activations on each feature map. This actually works a lot better in terms of retrieval, while practically having the same computational cost in matching, because the vectors are always of the same size, k. Right, so this is a very nice technique for using off-the-shelf networks for doing image search or vector search or whatever your data set may be. I mean, this can be applied. This principle can be easily applied for other types of data, not just images, depending on what the network has been trained on. So So normally people ask, okay, so since these features do so well without any training, can we actually get even further? I mean, even a bigger boost when we do a bit of training. So of course, and this was another major paper at the time. So this is really the days when deep learning has started to catch up. At that time, it was not so easy to have PyTorch. Frameworks were not so easily available, right? We didn't have so much open source implementations in PyTorch, in TensorFlow, Keras, or whatever your framework of choice might be. There was usually just some C++ code out there made by a student, which was working, but it was not necessarily easy for a newcomer to get along with. So it took a while. So this is why naturally people just used the networks as they were, and took the features and then connected it to something that they knew. So in this case, an SVM. So we connected the CNN representations with an SVM classifier, which it's just a particular type of classifier. You don't need to worry about what's inside. You might have seen it in some previous introduction to machine learning courses, and they train the classifier on top of it. So this is a bit of in contrast with what was common in computer vision at that time, where we had practically quite complex pipelines to deal with. So computer vision model at that time consisted of several blocks. So if I take here the components for object detection, practically we had to use different annotations for the parts of the object. Here DPM stands for deformable part models, where we allow the objects to have different degrees of deformation of moving parts. So imagine if you have a bike and the cyclist on it. So yeah, the cyclist might change in pose. We have some parts on the wheels on the bike, so they can move if in different ways. So we had a model to cover that. Then we needed to learn a canonical pose for each such deformation. Then we had some features that we introduced to the ESVM that was building on this. This model was relying actually on some edges in the image. So this was a very complex pipeline, and the most annoying thing is that there was no way of communicating the error here to the other blocks. So you always had to manually tune and use your expertise to better tune each part, the hyperparameters of each part, in order to get to a better outcome. While here with CNNs, it's just easy. You just use the CNN and train a linear classifier. Knowing that in this case right now, we just train a linear classifier on top of the CNN representation, so we don't go backward yet. We'll go next, but now in this case, we just use the last layer features and fine-tune and train a linear classifier on it. So what these authors did, then they took most of the popular computer vision benchmarks at the time, and say, can we actually come up with a baseline that is really effortless? Because we had to train the image on ImageNet, the network on ImageNet, but we just use these features. So in green, we see the state of the art at that time for each of these data sets. So we object classification. So here we have images of objects, and we need to put a label on that. Scene classification. Here we have images of scenes like outdoor, forest, dining room, bathroom, kitchen, and things like that. So we need to put a label there. Here is bird subcategorization. So we have different types of bird species, and we want to recognize finally each type of them. Same for flowers and so forth. So here we have buildings, sculptures, and here we have a retrieval, where we do nearest neighbor. So we have a query image, the scene, like and we want to find images of the same scene, like for example other images of the same metro station, for example, or the same train station. Well, here we have object instance retrieval, where we're looking for the same building or for the same person in a data set. And so we have in green best state of the art, off the shelf CNN with pink, with a darker with red CNN of the shelf plus some augmentations of the data, and having a spatialized CNN with which was trained for that. It's not always the case to have this one because it's not always easy. But we can see that in general, these new additions, even without any training, do already well. But then when we start fine tuning, it's already seeing a bit of a boost. And while not always outperforming the state of the art, we still see some significant improvements. So at that time, one of the authors was so excited about this. Stephen Carlson is the professor behind this paper, that he was practically saying that computer vision is now essentially solved. Which of course is not quite the case yet, but just to give you a bit of it was a bit of the unknown at that time. But when we people saw how well these things worked really off the shelf compared to some very complex computer vision models that we had at that time, it's normal that it's understandable that people got so excited. But there's just to assure you, there's still plenty of work in computer vision to be still done yet. A lot. So we're still far away from having it solved. So now we'll be speaking about fine tuning. So we'll go a bit further. We saw off-the-shelf networks. We saw what we can do when training just the final layer in just training a classifier on top of the outputs, which might be actually a good idea for some of the projects that we have this year. If you don't have much GPU, you can do that. You can take your data set of images, you pass them through a CNN, you store offline your features, which in this case can be 4,000 dimensional vectors of a length 4,000, and it's easy to make a data loader, and you feed that to a linear classifier, and it's a lot easier to train. Right? It's compared to always loading, unloading, and passing the images through the data set. So if you don't have much GPU resources, you can consider this as an option. So moving on further, so we want to adapt even further the network, not just the final layer. So this is what we call fine tuning, when we adjust our network to a new task. So we're again putting it into more formal words. So we assume here that the parameters of our CNNS are already well placed in a good start in the weight space and the optimization space to near our final local optimum. So we can use the values of these parameters of CNNS as the initial parameters for our new CNNT on this target dataset. And this is particularly appealing when dataset T is relatively big. Well, not so big. I wanted to say relatively small, but still not in the order of few samples, but in the order of a few thousand images across classes. So not necessarily a few thousand images per class, but in general, we have at least a few thousand images. So to compare that with ImageNet, which has 1 million images. So here, well, there's a bit of heuristics that we can think of. So depending on the size of this dataset T, we can decide. We're practically in fine tuning. We freeze some layers, and we let our optimization train update some of the final weights. And well, this is a very hand wavy sketch, but just to give you some idea. So when we have very little data, we just fine tune the final layer. When we have some more data, we can fine tune just the classification layers, the fully connected layers. And when you have a lot of data, we can decide to freeze just the first two convolution layers, and then let also some of the others to be fine tuned. So and this is kind of given this rule on which parts to update and which ones to not. Usually they depend on the size of dataset T. Sorry. So we can this allows us to decide which layers to freeze and which to fine tune or even replace. So as a rule of thumb, if the network is pre-trained, when we fine tune, we use a lower learning rate, about 10% of the original one, and for the new layers we can use also more aggressive learning rates, like the usual one. So if the dataset S and T are quite similar, we can fine-tune only the fully connected layer. So if you're still seeing the images of that you generally see on the web, like the ones trained on ImageNet, cats, dogs, well, various people, it's quite safe to fine-tune just the fully connected layers. However, if the data sets are different and you have more data, it's better to fine-tune all the layers. So to give you some example, again, our source image data set is ImageNet with images from the web. But then when you work on self-driving, you have images from the car mounted from a camera mounted on the car, and the scenes are quite different. The images are higher resolution, so then you might need some more augmented fine-tuning. Because well, even though it's still the real world, you might have quite a few differences. And well, I've seen some people actually were using it for even stronger differences between the images. For example, pre-trained on ImageNet, but then the target being some medical imaging. And apparently, this also works there to some extent. In some cases, they had to pre-train the network with grayscale images, such that it would be more compatible with the target dataset, or you can just convert the first convolution layer into, instead of having 3 channels, just to have 1, and then you just fine tune this one, and without necessarily without retraining completely on the entire ImageNet. So to help you out with the selection of which layers to freeze, you can refer to these types of visualizations. So this is a relatively old visualizations from ECCV 14, where the authors try to better understand the internal representations learned by the CNN. So they make some visualizations. So the visualization for layer 1 is a bit more specific. So here we first show them well, some filters, right? We have 9 filters, and then and we can visualize them, and then for each of the filters, so assume we have a test data set, or a set of images, and we pass them through the network, and we look at all the activations in the feature maps. So what we do here, we select the most salient patterns for this filter here. Here we select the 9 most salient patterns, the one with the highest activation for this filter here, and for this filter here, and so forth. So we can see here, for example, this is a green filter. So normally should the outputs to have maximum output should correspond to some green patches. So these are the patches that correspond to these high activations. We can see they're all green. Here we have this edge like this. So we can see that the highest active patterns, highest activation patterns correspond to patches correspond to this edge here. Here the edge is the other way around. So again, we can see it in this manner here. Here we have some color gradient mixed with an edge, so we can also visualize it here and so forth. So we can see that this corresponds to very raw low-level features. When we go upper in the network, we can no longer visualize the filters because they usually are they're not in 3D. They are in 128 to 56, 512 depth. So we cannot actually visualize the filters, but we can still visualize the patches that activate the most this filter. So here we can still we start to have more complex textures, patterns, but still coupled with some edge or contour information, right? So here we have these concentric circles that start appearing. Here we have this edge, but with this green pattern that appears. Here what we have is this basket-like pattern where we practically have pieces of wood that connect to each other. When we go deeper into the network towards the upper layers, we can see that some patterns are starting to emerge. Right? So here we can see that this filter is activating quite well when we see people, but people from the waist to the up, right? So half people we can start seeing here. Here is this type of crystal or feathers. I cannot figure exactly, but is this fluffy or stony white pattern? Here, this one starts to activate on something that looks like barcodes. And as we go deeper in the network, we can start well again complexifying and to see that we can start detecting specific type of objects. So here we can see the similar dog breed appearing. Here are some wheels, birds, and as we go further, the objects are becoming finer grained and more refined. So here we have bikes, different breed of dog, flowers, and so forth. So this might allow you to analyze better the differences between the ImageNet dataset and your dataset, and to see which layers you would want to freeze, right? So if your images don't contain any dogs or any types of objects that are in ImageNet, you might go to a lower layer, right? You might freeze, you might unfreeze these two and start fine tuning from here onwards, for example. So you might ask, so since we discovered last time, we discovered ResNet, how can you actually fine tune a ResNet? Because we have many more layers. We don't have just 10 layers as or 16 layers as an ImageNet. So here we have a 34 layer ResNet, and it's not the biggest one. What we do there, so you remember, I was saying that these convolutional neural architectures, even though they're way bigger, like you go out to 150 layers, you still have the roughly the same design principles. Namely, you have these 5 main convolutional blocks that you can actually see here in colors. So you have the final one, 5, 4, 3, 2, and 1, which is the first convolutional one, which is has a particular type of filter, 7 by 7. So you can apply the same principles of just freezing a certain block now. So since we have five blocks, it's a lot easier to resonate in these blocks and to freeze a certain block. So, well, now if you have big GPUs in some more considerate, more consistent amounts of data, selecting which layers to freeze is less of a problem. So in this case, common practice is to either freeze the entire network if you have really small data, or just freeze only the first 2 blocks, as we do in object detection for fine tuning. We take an ImageNet in an ImageNet, and then we fine tune it for another task, and we freeze just the first two blocks. And also, what is quite common is really to fine tune the entire network. Right? You use the lower learning rate and just fine tune the entire network without worrying less about what the network will freeze. But again, while I'm giving you all the options to better adapt it to your setting and your hardware and your dataset. So this, I cannot insist enough. In general, pre-trained networks are really everywhere, right? So if you look especially in academic papers, they're really the bread and butter in computer vision. Since what you will see in most computer vision papers is that in order to boost up scores and to train faster, people start from an ImageNet pre-trained model. So and also in industry starting to be the current, although not necessarily trained on ImageNet, on some internal data sets, and then you fine tune on some data sets for which you have less labels. This is shown to be work quite well. So just to give you an example for semantic segmentation, where your input is an image and the output is also a 2D map, which says for each pixel what class it is. So you have many more. So differently from image classification, where you had just one classification over the entire image, here we have as many classifications as pixels in the image. So here we have several architectures for semantic segmentation, which seems to be a novel task and different from ImageNet. So what do people do? These networks practically have a first part where they reduce the image, the feature maps, and then they go up back again to the original size of the image. So we call these hourglass architectures. So they have different. Although they have some slight differences, they kind of follow the same patterns. So the most known ones are these ones: SAGNet, UNet, PSPNet, and DeepLab. And all of them in the papers, when you look at this encoder part, so this part of the downsampling the images, they use a pre-trained ImageNet model. Right? And then for the decoding part, which is usually fewer layers, you start with random initialized weights. So in general, yeah, this is a good idea, especially for your projects, to start with a pre-trained network, because it will allow you to train faster and avoid the hassle of starting from scratch and having long training times. So next, we'll be speaking. So far we saw off-the-shelf networks and fine-tuning. So we'll be seeing a different way of doing task transfer learning when we no longer have the difference of a source data set and a target data set, but we actually have a source task and the target task. So this part is mostly based on one paper that initialized practically this field. Although in some cases it was known practice, but in this paper in Taskonomy they did a huge study on the impact on this area. So just to outline a bit the settings. So we know that some computer vision tasks are more interrelated than the others. So for example, the estimation of the depth. So meaning that you have an image and you want for each pixel to decide how far it is from the camera. So this task of depth estimation could help surface normal estimation. So in surface normal estimations, we want to see in a 3D world practically in which direction and which way is the normal heading for each type of the surface. So inherently they seem quite related, this because we also need at each time an information of the depth. The same if you look at scene layout. So how is the scene configured and what objects are in the image, or how are they placed with respect to each other, could help object detection where you want to localize a specific object in the image. And the whole point here of looking into task transfer learning is that for some tasks, the annotation or the data can be more easily obtainable than the others, right? So, for example, in a depth estimation, we can use a 3D sensor or a Kinect to give us the training data for cheap, and we can train our network on this data, and then we can fine tune it on some other tasks for which we don't have much data, right? So it's kind of the same principle as before, but here we're speaking more in terms of tasks. So so what the authors did here, they were trying to find a model that better decides without always the relying to human expertise how are tasks interconnected and which pairs are more adequate to use when going to such endeavors. So what they did, they created a huge data set. Well, it's mostly synthetic. They call it a task bank, where they have for a certain data for each image or video, they have annotations for 26 tasks. Some are semantic, some are concerned 2D, some concerned 3D. And then I said this data set is quite big. It has 4 million images. And each image, sorry, it's not synthetic. It's a real data set that they acquired indoors in. Well, it's a team from Stanford and Berkeley. It has 4 million real images, and each image has the ground truth for all these tasks. So what the authors did, they created 26 task specific networks where they trained for each of these tasks. They trained a dedicated network. So this is just a video to give you an idea on how are these tasks different from each other. So here we have 2D edges that we want to detect. So it's the contours in the image. Here we have the edges that occlude an object, so that we know that they hide something behind. These are the surface normals that I was telling you before, where we look at perpendicular directions for each surface that we have and how it's oriented. What we have here, colorization. So here we have the color information, because we might start from my black and white images, and then we want the task is to colorize the image. Here we have semantic segmentation, the one that I told you before, on which we want to classify each pixel in the image according to a known class of objects. Here we have the depth estimation, and so forth. So a lot of tasks. So here is object classification and scene classification. So this is quite a variety of tasks that we have here. So again, so the whole point was to test the impact on that one upstream task has on the downstream or target task, source task over the target task. So they use the common setting for all of them. So we have a ResNet 50 encoder, which is trained on one of the 26 tasks. And then in the second stage, we add a different decoder, and we initialize it from scratch, and we fine tune it on another target task. So we actually have here a lot less data. So here we use the entire data set for the first stage. Well, here the authors test with varying amounts, but always smaller amounts of training data. So to give you an idea, so for full training, we use the 120K images. So these are for validation and testing, and for fine tuning in the second stage, we use between 1 and 16K images. So you can see that we use a lot less images. So so what the authors did is it's an impressive endeavor and experiment, which I think did not so well to the planet, because I think they have accumulated about 800 GPU years for this paper. So they tested all combinations of tasks and fine tunings with different amounts of data, and at some point they were even coupling more source tasks, like here you could add curvature, depth estimation, and so forth. So they were using the features from different networks and fine-tuning this decoder. I remind that this part here is frozen, right? So they have frozen the encoder and just fine-tuned this decoder part. So they created this complex model of showing the impact of which task has on which, and they created this this taxonomy, which says when it's a good idea to use which task is more appropriate as a source for which task as target. So this is one of and they they derive this for various supervision budget, meaning how many images you can actually have. So depending on the supervision budget, you have a specific taxonomy that will allow you to train and to make better use of your data. So you can see that there's quite a few connections between different data sets. For example, curvature helps semantic segmentation and also helps matching. Semantic segmentation can help occlusion edges. If you have already the information from surface novels, it seems to be helping quite a few tasks. So it seems to be the most generic one in terms of helping. Well, if you use denoising, it helps to detecting then so denoising is when you add some noise in the input image and then you want to output the clean image, which is a very easy task. Easy to formalize, sorry, not necessarily easy to solve task, because you can generate as much data as you want. So this helps actually to detect to the edges and then to the key point. So you can I will let you have fun with the visualization. So there's a very nice website. I think I didn't add it here, where you can actually see all these representations. You can have access to some trained models and this taxonomy, and I'll let you have fun with it. And it's quite useful, particularly in robotics and in computer vision, when you have you have multiple sensors that you can rely on, and some can give you already annotated data that you can use then for some other data from some other tasks for which we have very few annotations. Another way of doing transfer learning, which is kind of related with task transfer learning, is what we call multitask learning. So I'm taking here an image from a person from a presentation from someone from Tesla, but this is quite common for all self-driving vehicles. So we have an image from a front camera, and this is the driver of the view, a driver's view. So if you have a self-driving car, actually there's many tasks to solve at the same time, right? So you need to look at for traffic lights and their state, right? You need to detect them, and then to detect on which state they are. Are they green? Are they either red? You need to detect overhead signs, right? So these signs which gives you the instructions on where to go or what what other instructions are on the road. Similarly, you have road signs which are on the ground. So if it's a construction site, you might have plenty of these. You might have various moving objects, cars or excavators here. You need to look at the road markings. You need to detect crosswalks. You need to detect curbs and lanes in general. Other static objects that you might have, and well, you can have all sorts of environment tags. So there's a lot of tasks to solve in the same time, right? And I guess you can all imagine that the resources on a car are well, you don't have these huge GPUs that you have in a data center, right? So what can we do there? So we know that we have to solve plenty of perception tasks simultaneously. So we have some options now. So we can either train multiple models, one for each task. But as I said, as I remind you, we don't have much resources on the car, so we will end up with very small models. And the annoying thing is that we have to, each time we add some new additions to our data, we have to retrain them again. So we have several trainings to do. Or another option, which is I think the most popular so far, is to inject all knowledge in the single model. So this is what we do with multitask learning. So to give you an idea on how does it actually happen in practice, so what the common setting for multitask learning is to have an encoder, which is like a backbone which is shared for all the tasks, and then at some point this encoder splits into multiple heads. So we have here at some point towards the end of the encoder, we have multiple heads that start to appear, and that are specialized for something for a specific task. So for example, here we have semantic segmentation, where we have one classification per pixel. We have instance segmentation, which is a bit different than semantic segmentation, meaning that, well, you can see here that their pedestrians are of different colors. So here we do pixel annotation, we pixel classification, but we also have to separate objects, right? So here we have to detect practically each pedestrian and to say this pixel here belongs to pedestrian 1, this to pedestrian 2, pedestrian 3, and so forth. While here you can see all pedestrians are red, are from the same class. Right? So it's a much more difficult task because it assumes also to detect accurately in the differences between the objects. And here we have a depth estimation. So we have here an encoder, a multitask pipeline with 3 tasks. So the way we train them, usually we train them simultaneously, these heads, and we sum their losses, and we have our multitask loss. So the whole point here is that on one hand we optimize our resources because we recycle this encoder and to learn and for getting predictions for all the tasks. But in the same time, we train a richer encoder because each task provides a more different and useful supervision for the network. And to some extent, we've seen it that it ensures also some more robustness because it's practically the network learns to look at the input data in different ways, right? So it looks at it from the perspective of semantic segmentation, from the perspective of depth estimation. So it gets this information about the depth, about the relative position of objects with respect to each other. But it also learns here, I guess, this view of how to better separate the objects in the scene. So this actually can be quite helpful. Well, we just don't simply, unfortunately, we don't simply sum over these losses. We usually have a weighted loss. So each task has a specific weight in order to find a good balance during training. So we have a weighted combination of these heads when we do training. So to give you an idea on how this actually occurs in PyTorch, so here I just made a very, very basic example with a linear practically one layer encoder, and then I've added two I've added two heads, right? Head 1 and head 2. They're kind of identical, just that they have different output size. And here we can see how it goes in the forward. Sorry. So in the forward, we have these shared features which are the output of the encoder, and we have one output from head 1 and an output two from head 2, and our networks returns two results, because it has two outputs. And then for training, it's mostly as before in terms of the training loop, just that we will need to have annotations for both tasks, right? So this is sometimes the computational can be one of the computational bottlenecks, because you need to load the data for each of the tasks. But here it's quite easy. We have just two tasks. We get our two outputs from our network, and we compute the losses for each corresponding task, and we weight them. And then, the automatic differentiation does its magic by backwarding, doing the backpropagating the gradient from the each corresponding head to the rest of the network. So in general, we usually have 2 to 5 tasks per network. In some cases, I've seen, at least in Tesla, they say they can have up to 50 tasks per network. This becomes complicated to train. So beyond 5 tasks, it becomes complicated to train in the same time. So what they do, they train for 5, maybe, let's say up to 10 tasks. Let's say they train simultaneously. Then, for example, let's say that we train just for traffic lights, and then what they do, you can freeze the backbone and this head, and just train this head. And then add this head with the entire pipeline frozen, and adding this head as well. Then you have these Hydra networks with many heads that work fast on the car. So the advantages of this approach is that it's really practical, and especially since we can share the encoder among many tasks, so we save a lot of computational time. And also we've seen that in general, multitask learning can lead to a better regularization, meaning that the network is less prone to overfitting, because it has these different types of supervision. On the downside, balancing these difficulties and the impact of each task is really non-trivial, right? So because each task might have different dynamics. Some might overfit faster, might be solved faster than the others, and might overfit, so impact the behavior for the others. The losses and the gradients for each one might be different, in particular the gradients. So there's quite a few approaches there that key aspects that they need to be addressed when training in multitask settings, especially since when tasks are relatively different and in different complexities. Some ideas to balance them would be to normalize the gradients from all the heads. So when the heads meet at the shared encoder, we can normalize the gradients and scale them such that they have very similar patterns, and then they can have an equal impact on the encoder. We can learn the weights on a per task basis, so we can have the weight for each head as a parameter of the network, and let the network learn these weights in our place. Or this is a paper from my group. We can learn a scheduling for training heads. So we use here meta learning, where we had another algorithm that was learning what would be the best strategy for training each head. So at some point, you can actually decide to stop one of the layers, one of the heads, and let just the others, because it might be too impacting, and then resume it again and stop another one, and so forth. So you can also have this types of strategy, but this is it remains a very, very practical approach, and I encourage you to look into it whenever you may think it might need it. So we're moving now to a final type of approaches for transfer learning, which is frequently confused with transfer learning, but it has some specificities that you will see in a minute. And this is the domain adaptation. So the confusion usually comes because, again, we have a source dataset and a target dataset. But here we assume that the differences between the source and the target dataset is major. Is quite significant, and and between the source and the target dataset, we have the same objects. So I'll be going to more specifics here. So imagine here that we want to do product classification. So we want to recognize what product and what object is in the image. And we take our images from Amazon or from a studio, and we can see that all our images that we use for training and that are annotated are very nice, very polished, white background, so it's easy to distinguish the object from the background because there's no background and so forth. Now our target dataset is it's a robotics dataset. So imagine that we have a robot moving in around the house. So these are the objects that are from the same images above, but in real world conditions, right? So we don't have any more good lighting. The objects are not placed in very canonical positions. We have the background, a lot of background, and we don't. For example, here we see the objects from the side, but usually the screen is from the front. So we have quite a big gap in terms of domain. So we call this the domain gap. And I forgot to say. So here we have internet images, and we want to have a model that works on a webcam. So this is what we see in an office compared to what we see on Amazon. In some other cases will be also when we have some synthetic images. So we want to recognize. This is what's done for Google for recognizing the Street View house numbers. So they had their own annotated data, but they would, in order to better recognize them, they also generated some synthetic data with all sorts of fonts, colors, blurring, and so forth, which can be used for generating additional training data and then to better adapt to real images. And some similar approaches were done also for a while ago for traffic sign recognition, where you had some synthetic or semi-synthetic traffic signs. Could be some real ones that we blurred out and that we complexified in order to get more data, and then to make it easier to generalize to adapt to real data. So in the deep learning era, I think most of the approaches for domain adaptation are derived from this major work, which is called domain adversarial networks. Where we try to train a network in such a manner that it will be easy to adapt, that will learn to adapt to this new target dataset. So we assume that in general for this real dataset, we either have very few labels or none. Right. So these are the usual settings. Most commonly, since it's in academic works, we assume we don't have any labels, but actually in practice we can have some labels, but of course very few compared to the source dataset. So I'll illustrate here the concept of domain adversarial networks. So as I said, we have two domains, right? So we have internet images and webcam images, right? So for internet images we have annotations. So this green part is the encoder, so it's our network encoder, and then with blue we have our classifier. So this does the classification of, well, so if we have here 5 objects to classify, it's a 5-way classification. So so this part is practically what we had before. We just separated them on colors to better see the differences between features and classifier. What's new in this types of work is that we have another head, which is called the domain classifier. So we have another branch in our network, whose task is to classify the domain of the input image, right? So it's a 2-way classifier, since we have 2 input domains: the source, which is internet images, and the target, which is office images, or webcam images. Sorry. So the goal here is to classify these 2 domains. However, well. And the intuition here is that what we want is to be bad at this task. So we want our network that takes these features to be not doing well at these tasks, so to practically confuse these 2 domains. And if we confuse these 2 domains, this means that the features here are equally good for both internet images and webcam images. So here for classification, if we don't have labels on the webcam images, we'll just use this branch just for our annotated images. while this domain classifier will use it for both domains. So in order to get to this trick, right, to minimizing this loss, but actually we want to maximize this loss. So what we do, what the contribution here is, what we is a gradient reversal layer. So here we train as usual, we minimize the loss, but at this point here we just flip the gradient, we let it go on the other side, on the opposite side, right? So we always want it to go on the side which will actually end up in confusing further this this domain classifier. So this will help us have features that, as I said, do equally well, that we hope to do equally well on target and on source images. So to give you a bit more details on how actually this works in the pipeline, so we build a network, right? So we define our network. In the first stage, we train our feature extractor in green and our class predictor on the source data, so on the internet images. We train the feature extractor and domain classifier on both the source and the target data. Right? So on the target data, we assume that we don't have images at this point, annotated images, sorry, labels. But well, you can easily see that if we at some point we have some classification, some labels, we can actually put it also into this pipeline, the target data. And then at test time, we just use the feature extractor and the class predictor. So at test time, we just remove this branch, and we care just about the classification performance. Well, so this is just to see how it's on a small image data set, like CFAR, how it looks like. So we have this classification head, and then we have this domain classifier head, which well has a relatively similar structure as the classification one. So we've seen this for image classification, and while I'm advertising here some areas of work of my group. So in autonomous driving, again, you might know that key data is key, right? And annotating such an image with the real by an annotator so complex thing like this one requires a bit up to 1.5 hours per image. Right? So this is really expensive and really time consuming, and we know that we need lots of images. So so what people have started looking into is into video games. Right? So here actually these images are snapshots from GTA 5. So an idea would be here is well, we know we can get from games are increasingly more realistic and have these complex graphics engines. So and also we have the information about the objects in the videos. So what if we in the game? So what if we use this data from games to do domain adaptation, right? So we get as many images as we want from these video games with accurate annotations. We use them as source, and then we want to transfer them on the images. Right. So yeah, this is what we call the large gap domain adaptation, because we have a big gap between these two domains, between video game images and real images. But there's actually things that we can do here to learn. So here we use these video games to generate training data, and we want to test them on real data. So so here I'm showing, well, if you just naively train on these video games data and then just test on real data, you get something like this. So here it's images on the output of a video game image, but then when we feed to this network a real image, we can see that the predictions are like that, right? So they're really messy. And here is just a confidence map or entropy maps in the prediction. So we can see that so whenever the points are more yellow or red, it means that the network is really uncertain. So there's a high entropy in the predictions. While when it's blue, it means that the network is quite confident. So you can see that the network outputs really messy results when just applied directly to real data. So my colleagues proposed a method that allows to practically to remove the entropy. So this is what their main intuition was, is to minimize the entropy during training, while when seeing these unlabeled real images, and end up with this type of prediction, which you can see is quite different from what we had before. Right? So you can see here the road is much cleaner. also the sidewalk, also the plants and so forth, compared to what we have before. So I'll give you a bit some details on how it works. So again, this is unsupervised domain adaptation. So meaning that we have access to the target images here with red arrows, but we don't have access to the labels. And the real images are with blue arrows. So we train our network to do semantic segmentation of this real images on this source images. Sorry, for which we have annotation. So here we have a segmentation loss. But their contribution is also here. So we minimize the entropy on the target images. As I said, it seems that there was a bigger entropy on these target images. So they had the loss that just minimizes the entropy. It's also a regularization. And it's a strategy that was used before in semi-supervised learning. And like we saw in domain adversarial networks, we train in an adversarial manner the network such that it will be confusing the two domains. Right? So it will not make the difference between these two the domains in terms of when looking at the features that are extracted from images from the two domains. It will not make a difference between them. So well, when you see these several branches and head, I mean, if you squint a bit, you might recognize some form of multitask learning here, right? So well, it's loosely, you can also think it as some form of multitask learning because you have different tasks and you train the network to optimize for multiple losses in the same time. So now when looking at the performances, so here they compare against so the Oracle is the model that is trained on in this case on cityscapes data, or using the annotations. Right, so UDA model is unsupervised domain adaptation model, which is trained on labeled images on GTA 5 and on unlabeled images on cityscapes. So it sees cityscapes images, but not the labels. So we can see that on the top we have a VGG16 encoder, on the bottom of ResNet 100 encoder. So we can see that actually, so this is the performance that we get with this approach, which is by the way named Advent. From adversarial entropy minimization, and we can see, well, we'll start to narrowing the gap. Okay, we're still far away because we're comparing synthetic images with real ones, but we have substantial computational gains in terms of annotation, and we can quickly integrate this and train it towards narrowing this gap. And these are some previous baselines that we had state-of-the-art methods at that time that this Advent method outperformed at the time. So I'll give you some example on unsupervised domain adaptation, on some qualitative examples. Sorry. So here we see some real images. This is the output of directly just training the network on synthetic images, and then these are two variants of Advent, where we can see that the results are substantially improved compared to the first ones, where it's really difficult to generalize from the synthetic images to real ones without any help, right? So you can see here it practically hallucinates cars everywhere, although we don't actually see much cars. I don't know why it fires on that, and same here. So I guess it's some of the biases in the network were probably in the game. There were a lot of cars in this part of the image. We did, well, they did the experiment also for fog, right? Again, so we had a bunch of foggy images, and well, we want to improve the performance there. So it's a new type of imagery, right? And we want to have good performance there. So what they did in this case, they trained on real images as source, and then they had some foggy images as target that were not labeled, and they applied practical Advent to the same setting, but here it's for object detection. So here it's the input, here is the output without any adaptation, and here is with the two variants. So you can see that here we can already start detecting the objects which were here and were not detected at all. These far away cars that were beyond the fog and that we couldn't see before. And here we even start detecting some pedestrians that were missed before. Same here, we start seeing further the cars beyond the fog, and to learn to recognize them also when there is fog. So while domain adaptation actually can have different applications in industry, because well, there will always be some new data that you haven't seen, or some new conditions that you want to address, or some new sensors. Your sensor might change, your camera might change to a different resolution or something like that, and it comes handy at that time to use domain adaptation. And finally, another type of domain adaptation that we can encounter in practice is to use to better exploit synthetic images by making them more realistic. So this is a nice paper from Apple, where they wanted to train a model that would detect where is the eye looking, the gaze, where is the eye looking in the on the camera, on the phone. So well, they need to make this robust to many types of clients, with glasses, without glasses, of different colors, with different specifics, and so forth. So and they had these graphics engines that could generate synthetic eyes. So and they had some unlabeled real images. So they trained the network to refine these synthetic images to make them look more realistic, without changing the ground truth, right? So the eye should be still looking at the same direction, because we want to use the annotations from there to train the model. So practically, they train the model in an adversarial manner to distort the real images and to make them more realistic. And this is what they achieve. And by injecting these images in the training, their performance improves quite a bit. And they showed a similar mechanism for well, if you're familiar with Kinect, for detecting gestures. And so these are depth maps of hands. So, for example, well, you might have seen in Kinect, this is what they do. They analyze these gestures, they compute these depth maps, and based on that, they recognize what gestures you are doing. So, of course, we have these synthetic examples, which are very perfect, but these do not correspond actually to the typical sensor output. So they train this distorter to distort these images to make them more realistic, and then train on them to get a performance boost. So this said, well, there's many flavors of transfer learning. So I've covered just a few of them. So I led this slide from this diagram from Tatiana Tomasi a few years ago, who did a very thorough splitting on the different types of domain adaptation that we have. We covered some of them today, namely the multitask, transfer learning across categories, domain adaptation over the same categories, and some covariate shift because of the types of the way the images are varying from one case to another, by training on the images of offices, on the internet, and then on offices. Well, we can also do some other types of transfers across tasks or features. So we covered this a bit to some extent in task transfer learning, but there are still a few areas that we didn't cover. I'll let you discover them in this nice thesis by Tatiana Tomasi if you want to go deeper into the topic. But I think we covered most of the popular ones, and I hope that they will be some useful tools for you in your projects and in your internships, or in your professional lives as deep learning practitioners. So I will conclude this module here, and in the next video we'll be speaking about self-supervised learning, which is a new type of approach for learning from learning to exploit large quantities of unlabeled images. So see you next, and thank you for your attention. Bye bye.